Hi there students, this is Dr. John, your physics and math professor, and today's video is especially for the super smart people who want to know more than all the other people in your class. Today I'm going to explain to you under what conditions this lens formula actually applies, which is 1 over f, which is equal to 1 over object, distance of the object, plus 1 over the distance of the image. All of this, we developed this in another video, all of this depends on the reality that if you have a ray of light coming in, the ray of light, and it hits this mirror, this concave mirror, this converging mirror, the light that reflects is going to hit this focal point, and the distance here is going to be the same as this distance x. It's going to be halfway to the center of curvature. The center of curvature, of course, would be also the radius at which you would create this circle, which would be the mirror in this case. For this specific illustration, I'm going to use a converging mirror. I could use a diverging mirror or a converging or diverging lens just as well. It's just easiest to see on this. So I'm going to give you a couple of examples, and we're going to show how we get to that result, under what conditions that result is true, and also under what conditions this formula works, and which really describes, we talk a lot about thin lenses and thin mirrors, what actually it means to have a thin lens or a thin mirror, at least one of the characteristics of it. So over here, I'm going to have this object here, which is fairly large compared to this circle. Notice here the center of curvature. I could actually create a whole circle, and this circle is mirrored. It's mirrored on the inside. This is an extremely high object compared to this mirror here. We're going to see what happens. So this thing comes in here, and notice it hits the mirror. Here's the normal to the mirror, which would be the r, the radius of curvature. So the normal here would hit here, and it hits at 45 degrees, or this angle up here is 45 degrees, which means that the ray of light also hits at 45 degrees, and it reflects at 45 degrees. So that means this is 45, this is 45. That would make this a right angle, a 90 degree. So if you have a 45 degree angle here and here, the length of this is the same as this length of this distance x here. You can do a simple calculation using the sine or cosine or tangent, and you're going to find that this distance x here is equal to the radius divided by the root of 2. And that ends up being 0.7 times r. Now remember, we said that this distance here or this distance here should be the same. Both of them should be 0.5 times c, or 0.5 times r. I'm using these interchangeably, r being the distance, the radius of the curvature here, c just being the center of curvature. It's more of a label. For this specific case here, r is equal to c, like I said here, with an extremely high object. This here, the distance from the center of curvature to here is 0.7 r, which means the focal length, in this case, if we want to call it that, the focal point would have a focal length of about 0.3 r, or 0.3 times to the center, which is definitely not in keeping with what we need to develop our lens formula. So let's go to a little bit shorter image. We'll shrink the image a little bit. This image is very high. Notice how high it hits. I'm going to shrink this image so it hits this mirror, still a very curved mirror, at 30 degrees up from the center of curvature. This one's 45, this one's 30. Now if it hits here at 30, this angle is also 30, and the angle of reflection is also 30, and it's going to hit here. We want to know this distance x. So what I've done here is I've flipped this upside down. This long blue line is r. This black line here is right over here, that's x, and this red line is over here. I've just taken this whole thing and flipped it over, and I'm just going to take this half of the triangle over here. And if you notice here that the cosine of 30 degrees here would equal to the adjacent, which is r over 2, divided by x, just like this. The cosine of 30 is r over 2 divided by x. Solve for x. I'm going to put the cosine of 30 over here like this, times 2, because that 2 goes in the denominator, and I'm going to get that equal to 0.577 times r. So this distance here is now 0.577 times r, which means this is a little less than half. So notice how as the image, the height of the object shrinks, it looks like we're getting closer. This distance here is getting closer to 0.5 r, which would also mean that the focal length here would be 0.5 r as well. Now these are two specific cases. Let's go to a general case, and I'm going to do something specific in this general case here, where I'm going to have the angle here, this angle over here, which I said was 30 degrees. I'm going to shrink this angle and make it much lower. I'm going to make this much lower, lower, lower. Now how low will I need to make it? I want to make it so that this angle here, the sine of this angle, is the same as that angle itself. Now, if you want to look at your calculator, you should find under the angle measurements, you'll find 3 different choices. You can find radians, you can find gradients, or you can find degrees. We're used to using degrees, but for most of our calculations like this, we want to use radians when we're actually doing the calculation. I just illustrated this with angles because it's a little easier for us to understand the degrees rather than putting these into radians. So when we're actually doing these calculations, we want to use radians. Now go into your calculator and punch in there, and to make your angle, your radian angle, smaller and smaller, and to see at what point the sine of that angle is very close to equal the angle itself, which is it's called the small angle approximation for sine. And what I did is I punched in a bunch of numbers, and I got down to sine of 0.3. That's equal to 0.2995, which is extremely close to 0.3. If you make this angle smaller than that, it's going to be practically equal. Sine of the angle basically equal to the angle itself. So 0.3 radians is about equal to 17 degrees. Now notice here, this is 30 degrees, so 17 degrees is about half of that. It's not ridiculously much smaller than that, but it's a little bit smaller than that. So now let's take a look at this diagram here. This is the same diagram I have over here, only notice I've made the curve here of the mirror extremely small. Of course, this doesn't reflect the actual curved distance here. The distance C would be much further back. I'm just trying to put it all into one board here so you can see it. The height of the image should, of course, be much smaller with respect to this distance C, but I just want you to be able to see it all over here. So this is an extremely small curve, but you can still see the curve here. The idea is that this distance C here is up to here of the lens is basically the same as the distance from here to here as well. It's basically identical. Over here, of course, that would not be the case. The distance from here to here is C or R. The distance from here to here is, of course, much less. That's one reason why we get this distortion. But over here, we're going to assume that this distance from here to here, the mirror, is almost the same as the distance from here to here. And that's going to come in a little bit in our calculation. For our previous examples, I had this angle alpha at 45 and at 30. I'm just going to give it a generic alpha now. Now, if this thing is this angle here, then this is also the same angle alpha over here. So once I've chosen this one becomes that. And this is the angle of incidence. So this is the ray of light coming in. This is the normal to the mirror, the R here. So that this is the angle of incidence. So this will be the angle of reflection. That'll be the same as well. So notice here inside this triangle, you have an alpha, you have another alpha, and the angles inside of a triangle have to add up to pi or 180. Pi radians or 180 degrees. So all the angles add up to pi, so that means this last angle has to be pi minus these two, pi minus 2 alpha. So I'm going to use this now, to find this x here, because if I can find this x, I can find this distance, which would be the distance to this point over here. So let's take a look at this. I'm going to use the sine formula for this. So here's the sine of alpha. That's the sine of this alpha over here, this one over here. The sine of this alpha over x. So the sine of this alpha over x is equal to the sine of pi minus 2 alpha, which is this here, over r. That is the sine formula where we take the sine of one of the angles over the opposing side and the side of the other angle over the opposing side. Those two are equal to each other, those ratios. You could flip these both upside down if you wanted to. And if you remember your sines, let's say your sine of 30 degrees here, up here, is the same as sine of 30 degrees up from here, or 150 this way. So the sine of pi minus some angle is the same as the sine of that angle. So I could just take this, the sine of pi minus 2 alpha, and make this the same as the sine of 2 alpha. This is the sine of alpha, sine of 2 alpha, and since I'm using this small angle approximation, sine of alpha is the same as alpha, and the sine of 2 alpha is the same as 2 alpha. Now flip both of these upside down, the alphas will cancel, and I'm going to be left with x equals r over 2. R being the radius of curvature here, or the distance to the center. So this distance x here is r over 2, which means this distance here is also r over 2. That's the focal point. So I've just shown you here how if we have a small angle, we can have the focal point being r over 2, or the distance c over 2, whichever one you want to call it here, which is this distance here. That's going to be the focal point. Now, what is this angle here? We talked over here about the fact that the angle itself has to be about 0.3. 0.3 is about 17 degrees. Remember here I used twice the angle. So the actual angle has to be half of 17 degrees, or 8 degrees. So if I take this 8 degrees, I put that into this little triangle. The h here is the height of the object. The c is the distance to the center of the curvature here. So that's sort of the ratio, because the height of the object is how high this comes in. That creates this angle of 8 degrees. H is the height of the object over c, the center of curvature, or the distance to the center of curvature. I could also use r. And if you take the tangent of this angle, the tangent of 8 is equal to h over c. So h over c is equal to the tangent of 8. The tangent of 8 is about 0.15. So the height of the object over the distance to the center of the curvature, or the radius of curvature, has to equal about 0.15. So if your center of curvature is, say, 10 centimeters, then your height of the object could be 1.5 centimeters. And as long as it's that height, or roughly that height, or a little bit smaller, this lens formula will apply, because the focal point will be right there. It'll start getting, it's far away from the focal point when the height is too high. It gets closer to that focal point, to the halfway between C and the mirror. And when you get to this height here, which is 8 degrees for this angle, or you make the height of the object over the distance to the center of curvature, or the radius of 0.5, when that height is small enough, you're going to create that focal point. It's going to stay there at that point. Also at that point, this mirror is practically flat and basically right here. So it's not like it's way over here. Like notice over here, this distance is much different. This distance is much different than this distance. But this distance here is going to be basically right there. So the distance from here to here is also going to be C. It's not going to be pushed out, as is the distance from here to here. So those are two contributions of thin lenses. All of them will happen if we have this arrangement here. So now you know more than all your other students. Like and subscribe and continue to learn, and I will see you in the next video. Bye-bye.